So what's an alternative? Effect size. I mean, it's not really an alternative. You should use both, please. Use both. There's no either or here. Just use both. It's helpful. Effect size is an index of the strength of the relationship between two variables. There are other ways to quantify it, but in personality, we're going to use correlation a lot. And a correlation can be used in either experimental or correlational studies. But it's a useful metric. It quantifies the strength of a relationship as well as the direction in a really nice way. So a correlation can be between -1 and 1. If you see a correlation outside those bounds, it's a covariance. Correlation is a standardized covariance. For the stats people in the room, that's it. Correlation coefficient is probably the most commonly used effect size. Like if you asked me to name one, I think that's the one. So correlation's less than 0, so negative correlation suggests that there's a negative association. So like increases in smoking are linked with decreases in longevity. So more smoking, less of the other thing. So that's a negative association, but it's a diagonal down. Positive association, correlations above 0. And the closer to a 1 or -1, the stronger it is. The more like predictive the association is, the more close and tightly together your data are. So positive associations like number of ice cream scoops or eaten, positively associated with happiness. Stuff like that. That's a lame example. Or how about this one? The likelihood that you are a cat lady is positively correlated with the number of cats you have. There we go. That I think is a really strong correlation. But that's the idea. And so stronger correlations are closer to the edges, and weaker correlations are closer to 0. A correlation of 0 means there's no relationship. So here's some illustrations. There's a fun game that I play in my intro stats class called Guess the Correlation. And I do it live in class because it's hard. Like, it's easy to be like, oh, perfectly correlated. -1. It goes straight down. 1 unit increase in X is associated with a 1 unit decrease in Y. A negative correlation of point -7, pretty close together. I know you've seen these. I'm just hammering it home again because it's helpful. No correlation, there's just a square blob. There's no systematic line. Here, 0.5, the dots are pretty close together, not super close, not as close as this guy. And here's perfect correlation. The dots perfectly lined up. So it's great for prediction. And interpreting the effect size, though, there's some disagreement, and David Foner has very strong opinions on this, and he's the only one that teaches this technique. It's not unuseful, so it can be used for prediction. So a 0.25 correlation, so small to medium, explains 25% of the variance in the relationship. But it's kind of hard to know what that means because it looks tiny. Because even a big correlation, so like a 0.9 correlation, means you explain 81% of the variance. A 0.9 correlation is huge. It's like really tightly lined up. And that's only 81%. But it's amazing. So it's not an effective metric. It gets misinterpreted and downplayed. Binomial effect size display, which I will keep spelling out the acronym for, is one method to kind of compare across different kinds of standardized effects that convert a correlation into an effect that looks closer to an experiment. So that when you're talking to experimentalists, if you have correlations, they just see that 0.25 or that 0.3, I cannot talk, like this, like a tiny correlation, tiny number, and be like, oh, that's small. 6 is tiny as a number. So clearly your work sucks. While I have these big numbers of percentages, but it's a way to understand the magnitude of a correlation and kind of help intuitively. This is not a universal opinion. I love R squared, but but I know how to interpret it because my advisor's specialty was literally the correlation. Yeah, here's the basic idea. Assume you have 200 participants with 100 in each group. What you do is concretely display what a correlation is in terms of a specific outcome. So, and ANOVA studies have the same structure. So here we have a correlation of 0. Each of these cells has 50 people in it. So the drug had no effect. So 50 people lived who took the drug, and 50 people lived who didn't take the drug. Same way as the other way. People who took the drug, 50-50. Out of 200 people, half live, half died. Correlation of 0.3, that's not huge. And if you were to take the square of that, it would be a number a little less than a number that I might put here. That is an exercise I will leave to the watcher. But you can convert this by just multiplying the correlation by 100 and dividing by 2. You're not going to have to be able to do this calculation, but it's the idea. And so a correlation of 0.3 shifts your finding from... So 35 people died who took this drug while 65 people lived. That's a 15-point difference. So if they didn't take the drug, only 35 of them lived. And that's a small correlation. Like, that's a 30-person difference, which is coincidence. Okay, it's coincidence these numbers work out that way. And that's a small effect. So that's our last little statistics unit. Unless you want more. I know you don't. I've read the course avails. But yeah, so that was statistics. Next time, for you at least, we're going to talk about some ethics.